If f has a power series representation at a, then the function f of x can be written as an infinite series. C sub n is a coefficient of an n term, x minus a will be the value at the center to the n power. This C sub n is a coefficient of the power series where you have f of the nth derivative evaluated at the center, which is your a value, over n factorial. This will give a function a Taylor series, and we can write it as the sum from 0 to infinity of f to the nth derivative. Now, if it's an original function, this is considered 0. 1 would be your first derivative. But anyway, it'll be your function evaluated at a over n factorial times x minus a to the n. If a equals 0, then we call it a Maclaurin series instead of a Taylor series. Then you'll just have an x to the n term instead of x minus the center. First example, find the Maclaurin series of f of x equals e to the 2x at the center value 0. What I like to do when I set these up is I take my original function, I write it down, and then I take anywhere from 3 to 4 derivatives. In this Taylor series, or what we're going to find as Maclaurin series, this coefficient is the pattern that we get established of n derivatives evaluated at the a value. So in this particular problem, I've taken the first 3 derivatives of our function. In the original and the 3 derivatives, I'm going to sub in 0. E to the 2 times 0 is 1. 2 times e to the 2 times 0, that's 2, and so forth. 4 times e to the 2 times 0, that's 4, and finally we get 8. Back up here, our Taylor series is the expansion and summation of these numerical values. So we have a 1, a 2, a 4, and an 8. If we keep going, we would have had like a 16, 32, and so forth. You want to make sure your list up here is long enough to where you can spot the pattern. N factorial, because the original function is considered a power of 0 as far as derivatives are concerned, we have 1 over 0 factorial times x to the 0 plus 2 over 1 factorial x to the first plus 4 over 2 factorial times x to the second, or squared, and then finally 8 over 3 factorial times x cubed. If we wrote a next term, it would be 16 over 4 factorial, x to the fourth, and so forth. Again, you want to go long enough to where you can spot the pattern. These upper left values that we found here, these are all powers of 2. So starting at 0, that's the original function, I'm going to write the sum from 0 to infinity of these numerators are powers of 2, so that's 2 to the n. The denominator is n factorial, and then our powers of x are n, because we have 0, 1, 2. Notice that your factorial and your power of x will match all the way through. If we combine these two terms, we can write this as the sum from 0 to infinity of 2x to the n. Just consolidate these two over n factorial. And this is the Taylor series representation of e to the 2x centered at 0. So we call it a Maclaurin series. Another example, find the Taylor series of the function sine x at the center pi. I'm going to take the original function, take 3 to 4 derivatives of it. When you get to the 4th or higher derivative, you can just put the order of the derivative in parentheses. This represents 4th derivative. Then, once you've made a pretty good list, 3 to 4 derivatives, then you sub in the center value into all of them. Sine of pi is 0, cosine of pi is -1, Negative sine of 0 is 0. Negative cosine pi is negative 1, which makes a positive 1. And then finally, we're back to sine x. That's the fourth derivative of pi. That's 0. These values in order, we have 0 over 0 factorial times x minus pi. We have a non-zero center to the 0 power, minus 1 over 1 factorial, x minus pi to the first, plus 0 over 2 factorial times x minus pi squared, plus 1 over 3 factorial times x minus pi cubed, plus 0 over 4 factorial times x minus pi to the fourth, and so on. Because this ends in sine, you just loop over and over. Taking out the 0 terms, you're left with negative 1 over 1 factorial times x minus pi, plus 1 over 3 factorial times x minus pi cubed. If I had bothered to take a fifth derivative, this would have led to negative 1 over 5 factorial times x minus pi to the fifth. And by now you can spot the pattern. All the even-powered terms go to 0. All the odd-powered terms remain. You have an alternating sign, negative, positive, negative, 1, 3, and 5, 1, 3, and 5. So writing this, sine x can be written as the sum from 0 to infinity of negative 1 to the n plus 1. Be very careful here. That has to be right. When you plug a 0 in, 0 plus 1 is 1. Negative 1 to the first is a negative. If we started off positive, you wouldn't use a plus 1. Because we've got to start off negative, we do. The remaining terms all have odd factorial values, 1, 3, and 5. If n is 0, we have 1 factorial. If n is 1, then we have 3 factorial. And finally, if n is 2, we have 5 factorial. So we know this term is right. Times x minus pi, and we have to make sure that our powers are odd. But since our powers match the factorial term, you can just copy that. 2n plus 1, that guarantees odds. If you were to change your index, this is totally fine and you don't have to change it. If you were to change your index to a 1, then you have to adjust your powers of n. 2 times 1 minus 1 is 1 factorial. 2 times 2 minus 1 is 3 factorial. And it doesn't take long to verify that if you slowly plug in values of n starting at 1, increasing 1, 2, 3, and so on, that this series will work just as well as that one. You have the option. And then finally, we'll look at the Taylor series for natural log of x centered at 1. Take our original function, several derivatives. I went ahead and made 5 derivatives of this one. Take your time to verify that the derivative of 1 over x is negative 1 over x squared. That derivative is 2 over x cubed. That derivative is negative 6 over x to the fourth, and so on. Once you've made sure that your list of derivatives is fine, then, starting with the original function and all the derivatives you've taken, substitute a 1 in. Natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 squared is negative 1. 2 over 1 cubed, that's 2, and so forth. You wind up with negative 6 and 24. All of these numerical values will become the numerator. 0, 1, negative 1, 2, negative 6, 24, and so on. After you get past this first term, your signs alternate, positive, negative, positive, negative. Because the first term has a numerical value of 0, that first term goes to 0. 1 over 1 factorial, that's 1, so we have x minus 1 to the first. 1 over 2 factorial is 2, so 1/2 x minus 1 squared. 2 over 3 factorial, 3 factorial is equal to 6. 2 over 6 is 3, x minus 1 cubed. 6 divided by 4 factorial, 4 factorial is 24. 6 over 24 is 1/4. And then finally, 24 over 5 factorial reduces to 1/5 times x minus 1 to the 5th, and then the pattern will continue. Ignoring the 0 term, I'm going to go ahead and start my index at a 1 because the 0 term is 0. Natural log of x centered at 1 can be written as the infinite series from 1 to infinity of -1 to the n plus 1. Again, be careful with your power of -1. Sub your number in. 1 plus 1 is 2. -1 squared is +1. Then when you move this up to 2, 2 plus 1 is 3. -1 to an odd power is negative. So we've got our sign alternator correct. Our denominator just worked out where once you reduced these fractions, your factorial went away. You actually had 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth. So you don't have the exclamation point, it's just n. Notice, they reduced, no more factorial. X minus 1, your center is at 1, so x minus 1 to those powers that increase 1 at a time. Notice your denominator and power match every time, so denominator and power match. X minus 1 tells us that 1's the center, and written this way, we get the correct sign alternation. I hope this video helps. Reach out if you have questions. Email, phone, stop by the office, and I'll do my best to help you out.